So our work here in section 6.4 is going to kind of start out with the work we did in section 6.3. And let me remind you what we did here, some of the big conclusions that we got out of that. And that would be that we started out with a population of size 5, just these 5 heights for some basketball players. And we didn't want to take the time to find the average for all 5 of these. Oh my gosh, that'd be a lot of work. So we got lazy. We took samples of size 2. And there was 5 choose 2 or 10 different samples of size 2. Now when we calculated the mean of all those different samples of size 2, the mean of these sample means actually turned out to be the mean of our population mean, which was 80. So the actual mean of our population was 80. But if you're sampling, you wouldn't know that. The idea behind sampling is that, all right, we need to estimate the population mean with our sample mean. And so for samples of size 2, these are all the different estimates you got. So not bad. But then we decide, okay, well, we won't be as lazy as just taking samples of size 2. We'll take samples of size 3 and then samples of size 4. And what we noticed was that whatever the sample size was, on average, these sample means, all these different sample means, actually had the mean of the population. So that made them an unbiased estimator, which was good. Now something else happened. As you increased your sample size, the spread of these variables, spread of this estimate of your sample population mean decreased. So as the sample size increases, the standard deviation of this random variable decreases. And by the way, that was one big thing that we remarked on, is that this is a random variable. The value of your sample mean just depends on chance. Now what we're going to do to start this next section, section 6.4, is we're going to repeat this kind of experiment, except with a lot more distributions. And to that end, I've got a nice link that I want to share with you. Let me see if I can't find it. Let's see. This one? No. Where is it? Give me a second. I got it here someplace. You know what? I know where I'll find it. Right here in one of our handouts. Should be at the top. There we go. So I'll put this link in the chat. If you want to open it up yourself, that's great. If not, that's fine too. Although it might be interesting for you to do so, because we're each going to get our own numbers. They all should be similar in a predictable way, but we're each going to get our own numbers. So let's just put that one in there. And you should get something that looks like this. And so let's start out with a uniform distribution. So when you get here, click the link in the bottom left of this box, and it's going to generate a uniform distribution. It has a mean of 200 and a standard deviation of 115.47. Okay. Now here's what's going to happen. We're going to take samples out of this population just like we did last week with the handout from section 6.3 and look at the distribution. So we'll start by taking samples of size 2. Now the computer is going to generate thousands of samples of size 2 and then plot the distribution. Now let's take a look at that distribution. There it is for me. Now the mean of my distribution is really close to the mean of its parent population. So that's 200. Although the standard deviation is a lot less. There's not as much spread in this data as there is in the population that we started out with. Okay. You guys should be seeing similar results. Is that true? Maybe not the exact same numbers, but more or less the same shape. This is the shape of the distribution of sample means for samples of size 2. Let's play this game again with samples of size 9. All right. So for 20,000 samples of size 9, we get a distribution that looks kind of like this. Now that's a little bit, different than what we just had. And it's even more different than what we just started out with. It's still symmetric, so it seems. Okay, take a look at its standard deviation. Standard deviation is 38.53. That's about 1/3 of what it was. So exactly 1/3 would be like 35.16 or something like that. So we're pretty close to about 1/3 of what it was. And we're going to keep going a few more times. Let's take a look at samples of size 25. It takes a second or two to generate those. Still, our sample mean has a distribution which has the same mean as our parent population, but now the standard deviation is about 1/5 of what it was. So if you divide this by 5, you're going to get this. Remind me, what does the standard deviation talk about? What does it measure?
How far the data is spread out from the mean.
Nice. Thanks, Joseph. How far the data is spread out from the mean. And the standard deviation here is much smaller than it is here, but take a look at the area in yellow. It's tighter around the mean than it is up here. Here, things are pretty spread out. It's a uniform distribution, but here it's a little bit tighter. So let's keep going. We're going to do the next two. Samples of size 36. Now the standard deviation is even smaller. Standard deviation is 19.29. So about 1/6 of what it was. Still has a nice symmetric shape. Almost looking normal there. Not perfect, but that's okay. And let's continue with this last one for samples of size 100. And wow. We're getting the same mean for our samples mean, for our sample mean, but a standard deviation which is 1/10 of what it started out as. So, wow. Now that's starting to become a little bit predictable, a little bit of a pattern there in terms of what's happening with the standard deviation, and I'll try and highlight that a little bit more in the next example. What you should be seeing here is that as the sample size increases, the sample standard deviation is decreasing, and the mean is still staying right around 200. So a couple things going on there. Let's do a new distribution. This time we'll pick one that's skewed left. This one has a mean of just under 300 and a standard deviation of 97.67. We're going to sample from this, starting with samples of size 9. Take a sample of size 9. We'll take thousands of samples of size 9. Each sample of size 9 is going to be one observation. We're going to calculate the mean of those samples of size 9 and then look at this distribution. So there you go. You have 20,000 samples of size 9. You calculate the mean of that distribution. This distribution of sample means for size 9 is pretty close to this one in terms of its population mean. 298, 297.96, pretty close. But what about the standard deviation here? standard deviation has been divided by 3. If you take this and divide by 3, you get roughly this. Now let's look at the distribution here. We started out with this distribution here, which was anything but normal. And now we've got something that's looking pretty close to normal. I'd say it's skewed a little bit to the left, but nowhere near as bad as the distribution we started with. How about a sample size 25? What's going to happen there? Any guesses?
It's going to become even thinner and taller.
Yep, thinner and taller. And look, the mean of these is really close to what we started out with in our what is called the parent population. Has nothing to do with me. Standard deviation is 1/5 of what it was. But increasingly, as the sample size increases, the distribution of the sample mean looks more and more normal. So you can see that for samples of size 36 and then size 100. For samples of size 36, if you take this standard deviation and divide it by 6, you get a little bit more than 16, which is perfect. If I do samples of size 100, I would expect that the distribution that I'll get is going to have a mean really close to this 297.96 and a standard deviation that's probably around 9.7 something. So let's see here. Should I be playing the lottery today because I'm a good forecaster? We'll find out.
Hey.
If we round this to the nearest 10th, that'd round up to 9.7. So yay. Time to play the lottery. Why not? Somebody's got to win. Why not you? Yay.
I have a quick question, if that's okay.
Yeah, please. Yeah.
So just kind of in relation to like how we're talking about the shapes of the distribution and then the graph ahead of that, kind of by just referencing the homework assignment that was on Google Sheets. One of the questions was saying like, what shape does the graph have for Benford's law? And I guess I just need a little clarification. I mean, are we supposed to be writing like skewed left or is it normal?
Well,
or I meant skewed right was, sorry.
Well, can you tell the difference between these two? I mean, which one is skewed left and which one's normal? Or at least
I would look at the bottom one and think more normal, except it is all the way skewed left. So like, I just don't.
Well, so the top one is skewed to the left and the bottom one has more of a normal distribution. Now, this is just a numerical simulation. It's not perfect. I'd like to see something a little bit better, but you know, it's not always going to happen when you're generating data dynamically. Now, typically speaking, what you'd like to see is something like what I'd see here. This is a normal distribution. Let me change the standard deviation. Standard deviation, if you remember, talks about the spread of the data. And if I increase my standard deviation, then I'm increasing the spread. So this is more spread out. So that's one of the things that you should be seeing as we increase our sample size. The sample standard deviation is decreasing. Or the distribution or the standard deviation of the sample means for a particular size is decreasing. And what that's doing is it's making our distribution taller and narrower. So that way you're concentrating all the probability near one point, near the mean. But if the standard deviation is bigger, that's more spread out. So that's definitely one thing that you should be seeing from this. As far as what you should be seeing on your assignment from Google Sheets, yeah, you're going to get something that you're familiar with, skewed left, skewed right, uniform, or normal. So one of your answers, or your answer should come from one of those above. Does that help out, Molly?
It does, yes, thank you.
Okay, appreciate the question. Now, To finish this up, I'm going to pick a normal distribution. If I sampled from a normal distribution, and let's take samples of size 9 to begin with, then right away I've got something which is normally distributed. So even though, doesn't matter what sample size I start out with, if I'm sampling from something that has a normal distribution, I'm going to get a normal distribution in return. It's just that it's going to be taller and narrower as I increase my sample size. So there you go. Now this all happens in a predictable way. Now let me share with you what's going to go on in the form of the central limit theorem. This is kind of an informal way to write it. But here's what's going to happen. There's two kind of cases that we're going to deal with. The first one is that if X is distributed normally with a mean of mu and a standard deviation of sigma, then for samples of size n, X bar is itself going to have a normal distribution. So let's write X bar sub n, just to remind ourselves that it's samples of size n. They're going to be distributed normally with the same mean as this parent population. But the standard deviation decreased, and it decreased in a predictable way. So the standard deviation, you might remember I made a little bold prediction with the last set of examples. I said, oh, well, the standard deviation is going to be 9.7. If I went over to n equals 36, I think the standard deviation would be about 11 and change. So let's take a look at that. Come on, there we go. So 11.19. So how am I getting that? Well, the standard deviation is this number, standard deviation of your parent population divided by the square root of n. So it's going to be sigma divided by the square root of your sample size. So that's for samples of size n coming from a normal distribution. What if you don't have a normal distribution to start with? Well, if you don't have a normal distribution to start with, eventually X bar sub n does have a distribution that looks normal. And, you know, it's going to kind of depend on what distribution to start with. But when your sample size gets up to at least 30, then the distribution of your sample mean is going to look normal no matter how awful your initial population or parent population was. So in this one, X is distributed with a mean of mu and a standard deviation sigma. Not necessarily normal anymore. In fact, let's assume it's not normal. So there's no n here. Just has a mean of mu and a standard deviation of sigma. Then for samples of size n, X bar sub n is going to be distributed normally with a mean of mu and a standard deviation of sigma over the square root of n. So one way or another, if you start out with a normal distribution, or if you start with something that's not a normal distribution, for samples of size at least 30, you're going to have a sample mean with an approximate normal distribution. And we saw that. We saw that with skewed left. We saw that with normal distributions. We saw that with uniform distribution, that when you look at the distribution of the sample mean, for large enough sample sizes, it has a normal distribution. So we're going to work with those kinds of problems. Okay. So that's the basis of our work in section 6.4.
Okay, so the second one would be considered not normal distribution then.
Yeah, this can be any distribution.
Okay.
Basically, any distribution. Yeah, it doesn't matter what your initial population is. When you get to samples of size 30 and more, that sample mean is going to have a normal distribution. But just to kind of remind you, we were looking at that for samples of size 2 and samples of size 3 back from this population. All right, but that wasn't normally distributed to begin with. But if we could take large enough samples out of that, you know, at samples of size 30 or more, you should start to get a normal distribution from all your different samples of size 30 or more. Obviously, you can't do that for such a small population, but that's what would happen. Okay, let's take a look at a couple examples. I sent your handout, and I realized after I sent that I made a mistake in it. So a couple of these problems are going to get modified, including part A, or example A, and example D. Now, one thing about Marty is that he uses real data. And I do remember a couple instances over the last few years where boats have capsized because they've been overloaded. There was one out west someplace and one in like New Jersey where a boat capsized because it was overloaded. And what's happened is that a lot of the assumptions that were made when they first created standards for these boats have changed. So the mean weight of people is no longer 132 pounds, more like 175 pounds. So let's look at some probabilities here. And what I want to note for us first is that we're going to assume that weights of people are normally distributed with a mean of 180.6 and a standard deviation of 36.1 pounds. So I'm going to start with that by writing that down. Mean of 180.6 and a standard deviation of 30, where was it, 36.1? Yeah, 36.1 pounds. So like that. Now, a lot of these boats are going to be overloaded if they have too much weight. That is, your average passenger is weighing more than, say, 175. So let's look at the probability that somebody weighs more than 175 pounds. So here's my normal distribution. Can someone tell me what number I should put right here for the center line? What should that be?
180.
Thank you. 180.6. Yeah. Now, if I'm looking for the probability that x is greater than 175, p of x greater than or equal to 175, well, first of all, 175 has to be drawn where on this curve? To the left, to the right of 180.6? To
The left.
the left, thank you. 175. All right, good. Now, someone else tell me, what area am I going to shade? To the left of 175 or to the right of 175?
To the right.
To the right. Nice. Cool. Let's keep it going. To the right. Now, as I shade all this, can someone else tell me?
I got a question.
Yeah, please.
Why would it be to the right?
Because I want the probability that x is greater than or equal to 175. So that's bigger numbers are going to be to the right.
Okay, thank you.
Okay, good. So can someone tell me if this probability is going to be bigger than 1/2 or less than 1/2?
Bigger.
I got a vote from Natasha that says bigger. Do we agree?
I agree.
Yes.
Yeah.
I-
Yeah, because the area to the right of 180.6 is going to be 1/2. And we've got more than just that area. So this has to be bigger than 1/2. Now, why do I mention that? I mention that because some of you who use Google Sheets might end up with the wrong area. If you did, you should be able to look back at your drawing here and go, oh, wait a minute, that doesn't make sense. I expect something greater than 1/2. Now, I'll do the first one on Google Sheets. I'll do the next one on the graphing calculator so that everyone gets a turn to see their technology used. Keep in mind that Google Sheets gives you the area to the left of something. So if you want to write the equals, leave yourself some space, and then I'll write equals norm distribution. Leave that little space there for me. And then I got to type my x value, which is 175. Then the mean, 180.6. Standard deviation is 36.1. And then true. Except, that's just going to give me the area to the left of 175.
You do 1 minus.
1 minus.
Ah, good. Because remember, the total area is 1. So what you wanted, and why I wanted you to leave that little thing there, was you want 1 minus that. So if you want to see what it looks like in Google Sheets, let me find that for us here. There we go. So Google Sheets. No, that's not it. All right, let me get rid of that. And that, and that. We'll just type in example A. And you can do it directly. You can just do it as 1 minus that. Sometimes people are going to break it up into 2 parts. Norm distribution, 175, and then 180.6, 36.1, and true. And you look at that and go, wait a minute, oh, there's something wrong there. Oh, I forgot to subtract from 1. So you do equals 1 minus, bam, that. And there you go. So you're about 56.16, something like that. So 0.5616 or 56.16%. Are you able to get that with your favorite technology?
I got a 55.4%. I use it.
I think I've got everything typed in correctly here. Someone else getting the same thing? Tell you what, let's just double check it on the graphing calculator then. So on the graphing calculator, I'll do it up on this one. Let me clear out a couple things here, here. So on the graphing calculator, it would look like this. Second distribution. You want normal CDF. We will not use normal PDF in this course. The lower limit is 175. The upper limit, you're just going to make something really, really big. The mean is 180.6. And the standard deviation is 36.1. And then when you're done, paste that in. If you have a TI-83 or something that doesn't give you the nice menu-driven stuff that I've got, you're just going to type in the normal CDF command, 175, comma, really big number, comma, mean, comma, standard deviation. So, yeah, I'm thinking 56.16. Maybe, Joe, that You accidentally typed in the wrong number someplace?
I did the same thing, except I just did 1 times e times 99 for the upper limit.
It's
Bless you.
I think it's the
Um,
lower limit that is supposed to be higher.
all
Lower
right,
limit
so
should be 175,
Or,
right?
yeah, lower is
175.
175 and then the 1,000 or the 1 million for upper.
Yeah, I did 1 times e times 99. Does that
well,
matter?
that's a little different. I mean, I'm not sure exactly how you're entering that in, but if you really want to enter
Yeah, you're right.
1899, then here's how it would look. Let me go back here. To do that EE stuff, you have to hit the second key, and then the comma. And take a look right above the second key and the comma. That gives you E99. And then I can delete all these. Better delete all those. And that's really what you want. That's about as close as you can get to infinity on this calculator. And I'm still getting the same thing.
Second divide, so I just pressed the wrong e, it seems.
Okay, cool. All right, but I appreciate the question and a chance to show off some calculator skills. So thank you. All right. Let's keep going. Now there's a part B to this, and I'm just going to kind of describe to you my own part B version of this. And that is, what if we looked at samples of size 50 for this population? So for n equal 50, samples of size 50, let's look at the distribution of sample means. So you're taking 50 people and saying, okay, let's look at the average of these 50 people. That's going to be a random variable. It's going to have the same mean that we did over here, 180.6, but the standard deviation is going to change. It's going to be 36.1 divided by the square root of 50. 36.1 divided by square root of 50 is about 5.105. So by taking a sample from this distribution, I've changed the distribution of the sample mean. I'm no longer working with this distribution. I've got a distribution that's narrower. So if I was to draw this, it'd be a really tight line up and down around 180.6. But I can't draw it wonderfully. I'll try and draw it a little bit to scale here, maybe. I knew I'd struggle with that. So it's a much narrower distribution. So I've got my 180.6 here. 175 is still over to the left, but there's probably a lot less area to the left of this and a lot more area to the right of this. So we'll figure out just how much in a second. The big thing to see, though, is that I'm working with a different distribution. That because I'm working with the sample mean for samples of size 50, that changes the shape of the curve that I've got here. Take the standard deviation from here, divided by the square root of the sample size. All right, so let's see if we can't do this one. Find the area here. Do you expect a bigger probability or a smaller probability when we do this one? Something bigger than 0.56 or smaller than 0.56? Well, it's not drawn wonderfully to scale, so if you're not sure, that's okay.
Would it be bigger than 0.56?
I'm thinking it's going to be bigger than 0.56. Yeah, thank you. Yeah, because there's more area concentrated around this, which is going to mean less area to the left of 175. All right, so let's see if we can't calculate this one on, I don't know, want to do the graphic calculator again? Or Google Sheets? We'll do them both. So on a graphing calculator, second vars, normal CDF. The lower limit is still 175. The upper limit is, I don't know, just a million or something really, really big. You don't have to get fancy with the 1E99. The mean is 180.6 and the standard deviation is 5.101 or 105. And we'll paste that in. So probability that X is greater than 175 here is a lot higher. Approximately 0.8637. Yeah. You could also do that in Google Sheets. Let's look at it there. So I'm just going to take this one and copy it. I'll paste it here, except I'm going to divide this by the square root of 50. And you can also type in 5.105. There's nothing wrong with that. Now, of course, you look at that and go, wait a minute, there's something wrong. The something wrong is we forgot to subtract it from 1. So now you can do that all in one command. It doesn't have to be spread out over two different commands. You can do it all at once if you'd like. So, all right, so I'm getting the same thing both times, so that's good. It's reassuring. Are you comfortable with getting this number out of your favorite technology?
Yep.
All right.
Yeah.
Yep.
Yeah.
Thank you. Thank you. Appreciate that. Let's try some more. So that was example A. Let's try example B. And I think this one is kind of the way I'd like it on your handout. So an airliner carries 350 passengers and has doors with heights of 72 inches. Heights of men are normally distributed with a mean of 69 and a standard deviation of 2.8. Let's stop right there. Let's write that down. So this is example B. X are distributed normally with a mean of 69 and a standard deviation of 2.8. Okay, so we want to start out with that. I think it was somebody in one of my morning classes here that suggested, you know what? I made a little template. And so every time she wants to draw a normal curve in her notes, she just kind of traces that out. It's a good idea.
That was me.
Yeah.
That's me.
Good job. Yeah, I like that idea. I haven't done it yet, but that's a good idea. All right. That's not too bad. I always tend to leave the right tail a little bit thicker than the left. So this middle number is 69. We want to find the probability that somebody has a height less than 72 inches, that is less than the height of the door. So let's just double check on that. If a male passenger is selected at random, find the probability that he can fit through the doorway without bending. That means that that male passenger's height is less than 72. So probability X is less than or equal to 72. That's what we're looking for. So let's put our 72 out here. Which way am I going to shade this? To the left or to the right?
Left.
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 Good. I want people that are shorter than 6 feet. So that's all this area here. And that's actually kind of good news for you Google Sheets users, because you don't have to worry about subtracting from 1. This is what Google Sheets gives you, is the area to the left. So, okay. Let's see if we can't find that area. Now, the big thing to notice about this kind of a part A here, to example B, is that you're just dealing with one person from this sample. So, all right. Why don't you see if you can't find that area? Find the area to the left of 72. I don't know about you, but I expect a number that's less than, or that's greater than anything. Can anyone fill that in? Number that's greater than?
Greater than 1/2.
Greater than 1/2. Wonderful. Yeah, you should get something bigger than 1/2, because this is to the right of your halfway point, 69. Thanks, Joseph. All right. Equals norm distribution of 72, comma 69, comma 2.8, comma true. And like I said, the good thing is you don't have to subtract from 1. Should just be good to go here. What are we getting on that? You guys getting some numbers? Throw one up.
0.8580.
So you have 0.8580?
Yes.
All right, cool. 8580. I'm getting the same thing. That's exactly what I'm getting. And if you wanted to see it in Google Sheets, let me jump over here for you. There you go. Right there. And here's your number, 0.8580.
Can we do it on the calculator?
Sure. So on the calculator, here's another cool trick for you guys, just to save yourself some time. If you hit second and then enter, it'll bring up your previous calculation. And all I'm going to do is go back and modify it a little bit. Now I got to be a little bit thoughtful. I need a lower estimate, a lower bound, and then an upper bound. So for my lower one, I'm going to type in -1 million. And I'm just going to hit a bunch of zeros. I don't really actually count to make sure that I've got 6. So it's your lower limit and then your upper limit. Now, Tony, what's our upper limit in this particular case?
72.
Yep, 72. So lower limit, then upper limit, so 72, comma, the mean was 69, comma, the standard deviation is 2.8.
I was getting like a negative.
If you get a negative, there's definitely a big problem there, because we shouldn't be getting a negative. Just so you know, there's also a delete key here. I can delete that one, and then I'm good. Looks like I'm getting the same thing that we got with Google Sheets, which is nice.
Wait,
Did that help?
What one did you delete, you said?
Oh, there was just a 1 left over from my previous calculation, so I just deleted that. But if you wanted to see that calculation again, that's what it would look like. So normal CDF of a really big negative number, 72, comma, 69, comma, 2.8.
So I have a question. Can we type in the like 1 million? Is it because I'm not doing that as a negative?
Oh, if you're getting an error when you try and type it in, you might be trying to use the subtraction sign to type in a -1 million instead of the opposite sign. So if you use the subtraction sign to put in your negative 1 million, it's going to balk at you. It's not going to like that.
Okay.
So try. Is that the issue?
I'm not sure. Okay, so lower limit is 1.
I did mine on calculator too. Mine was I did mine different, but I got the same answer.
Okay. You don't have to use negative 1 million. If you use negative 1,000, it'll still probably work out okay. Or you could, if you really wanted to be absolute about it, you could type in negative 1 and then second comma. That puts you in scientific notation. So it's negative 1 times 10 to the 99th power. And then I'll delete these, delete. And again, I should get the same answer. So there's a lot of numbers you can use for the lower bound. Just as long as it's far enough out there, it'll trick the calculator into thinking it's negative infinity.
I got it. It was just that I wasn't putting in negative like 1,000 or negative 1 million. It was just popping in
Okay.
as just 1 million. So
Okay, there you go.
yeah. So anytime we do the lower limit, we just I have to remember to put in the negative.
Yep.
Okay.
Good. Now, there's a second part to this problem that I want to get at, and that is if half of the passengers, so 175, if half the passengers are men, find the probability that the mean height of 175 men is less than 72. So let's write down something important here for part B. And that is n equals 175. And now we're going to look at this problem again, except we're going to look at the sample distribution of sample means for samples of size 175. So, okay. Well, this is going to have a normal distribution for 2 reasons. 1, the sample size is large enough, it's greater than 30. And 2, it's coming from a population which is normally distributed to begin with. So this definitely has a normal distribution. And let's find out some more about that normal distribution. Something like that. Kind of looks like a wave instead of a nice bell shape, but yeah, sorry about that. Let's account for the mean, which is going to be my 186. Excuse me, no, sorry, wrong problem. 69. Now, really, the standard deviation should have shrunk. The mean of this new random variable, what is it? Can someone help me out? What's the mean going to be here?
Is it still 69?
Yes, it is still 69. What is going to change, though, is the standard deviation. So standard deviation is going to be the old standard deviation of 2.8 divided by the square root of what?
175.
175. Nice. And that's going to be about 0.2117. Not sure you need all those digits, but we got them. So what's happened is that your standard deviation has shrunk dramatically. Okay. We still want to find, the area to the left of 72. So I still want this area to the left. I've just got a new curve here. Now keep an eye out on an exam. I might ask you to actually draw some of these curves. And the only reason I really do it is because I want to guide your intuition. I want to make sure that you expect a number that's bigger than 1/2. All right, so that if you get something that's smaller than 1/2, you go, wait a minute, there's something wrong. So we can do this one kind of like we did this one over here, equals norm distribution 72, 69, 2.8 over the square root of 175, comma true. Or you could just type in 0.2117, probably be just as easy to do that. So instead of this, we'll type in 0.2117. I might do it the other way on Google Sheets just so that if anyone's coming behind me, they can kind of see where this is coming from a little bit easier. There we go. No, sample B. Here we go. So there it is on Google Sheets. Your part B here. And it's so close to 1 that it actually rounds it up to 1. It just says, you know what? That's just 1. And we're going to leave it there. So interesting. So that probability is about 1. At least rounded down to 4 digits.
Can you do a calculator?
Mm-hmm. So on a calculator, well, it's really going to be convenient on a calculator. If you hit the second key, then the enter key, it'll bring up your last calculation. And the only thing I got to do is I got to change the standard deviation. So I could either divide that by the square root of 175, or I could just type in 0.2117 and get it that way. So, and you don't have to have -1 E99. You can type in -1,000,000. That'd be fine. I always just go with -1,000,000 because it's a nice round number. You could probably get away with like -1,000 if you wanted to, but I just -1,000,000 is a nice, easy number. Jaleisha, did that help out?
Yes, thank you.
All right, cool. Thank you. Anything else on this one? Are you guys able to get that number?
Yep.
All right. Thank you, Alex.